In section 3.2, we're going to learn how to find the probability of two events that occur in sequence one after the other. So this is usually referred to as a conditional probability, which is the probability of an event occurring given that another event has already occurred. So the conditional probability of event B happening, given that event A has happened, is denoted by, and you'll see the notation here, the probability of B given A is how we read that notation. Example 1 involves a standard deck of 52 cards, and I always find I have some people who aren't familiar with all of the cards in the deck and the suits, so I've given you a visual that shows you that information. So example 1 says 2 cards are selected in sequence from a standard deck of 52 playing cards. Find the probability that the second card is a queen, given that the first card is a king. And then it says assume that the king is not replaced. Meaning, if the first card comes up as a king, they're saying don't replace it, don't put it back into the deck when you choose your second card. My first event, event A, is going to be selecting a king, and the second event is choosing a queen. So what I'm looking for is the probability of getting a queen given that a king has already been chosen and not replaced. If I have taken a king out of the deck, you can see the 52 cards up above here. So if I take one king out of the deck, my denominator for my fraction should be the total number of possible cards that are remaining for me to choose on my second draw, which would be 51. Then on the numerator should be the probability that I do get the outcome I want, which is a queen. So when I look at the queen column, there's 4 different suits, so there's 4 different queens. So this probability should be written as 4 out of 51. And when you pick up a calculator, that's approximately 0.08 or 8% chance that if your first pick is a king, your second pick will be a queen. In a slightly different example here, we've got a table of values of survey results from 2,276 social media users, and they were asked whether or not they've been offended by something they saw on social media. We're asked to find the probability that a user is male, given that, so this is the thing that's already happened, the user was offended. So my event A, the one that has already occurred, the user was offended. And then I want to know of those, what's the probability of being a male in this survey? So I want the probability of being male given that you're a user who was offended. And in order to do that, you need to know, first of all, how many people were offended. So if you look at this table here, we have a yes, a no, and a total. For my denominator, I'm not going to use this total number because that represents both those who were offended and were not. With a conditional probability, I assume that I got a yes response. So I'm assuming that this probability then is only out of a pool of 1,151. And of those 1,151, 532 were male. So the probability of being male then, again, if you pick up a calculator, you're going to get approximately 0.46 or a 46% chance that if you knew somebody responded they were offended, there's a 46% chance that person would be male. We need to make a distinction, though, between whether or not the first probability, the probability of the first event, affects the probability of what can happen on the second event. So in some experiments, one event doesn't affect the probability of another. In this case, they're called independent events. For example, if you flip a coin, the probability of getting heads on your second flip doesn't change based on what you got on the first flip. Every single flip of the coin is always a 50% chance of getting heads. So we consider those to be independent events because no matter what happened on the first flip, getting heads on the second flip is still a 50% chance. We can tell if two events are independent, sometimes just using our own common sense, and other times we rely on this formula. Two events A and B are independent when the probability of B, given that A has already happened, is the same as the probability of B, meaning the first event then didn't affect the probability. Or we can switch it up and say it the other way. The probability of A, given that event B has already happened, is the same as the probability of A, meaning event B didn't affect the probability of A. If your events are not independent, then we call them dependent. So let's look at some examples of this to make that clear. Determine whether the events are independent or dependent. It says selecting a king is event A from a standard deck of 52 playing cards, not replacing it, and then selecting a queen, that's event B from the deck. So in this case, we want to determine the probability of B given A. In other words, the probability of getting a queen given that our first pick was a king. We already calculated that probability previously in the last example, and we said if you take that king out, then when it comes time to draw a queen, there are only 51 cards left, and 4 of those are queens. Now, what this definition up above says is now we want to compare that to the probability of just event B happening by itself. So now the question is, what's the probability of just picking a queen? Now, again, we don't include any part of event A happening. We just say, what's the probability of picking a queen from a deck of cards? Well, there are normally 52 cards, and 4 of them are queens. So in this case, because the probability of B given A is not the same as just the probability of B, we know that this first event, event A, did have an effect. And it specifically had an effect because we were told not to put the card back in the deck. That makes A and B dependent events. Now, in the next example, our event A is tossing a coin and getting ahead, and then rolling a 6-sided die and obtaining a 6, event B. This is where your common sense should kind of step in and say, okay, if I flip a coin first and then roll a 6-sided die, does the outcome on the coin affect what outcome I'm going to get when I roll the die? You should automatically kind of feel like, no, these are going to be independent events. But in order to verify that, we're going to do the same thing as the last example, where it says first we're tossing the coin, then we're rolling the die. So the probability of rolling a 6-sided die and getting a 6, given that I've tossed a coin and gotten ahead. Well, let's think about that. If I tossed the coin and got ahead, has that affected the outcomes on the die? No, there are still 6 outcomes, and only one of the 6 sides is labeled with a 6. So that has a probability of 1 out of 6 of happening. Now I need to compare that to the probability of just B happening by itself. So just rolling a 6-sided die and getting a 6. That's also 1 out of 6. So in this case, because A did not have any effect whatsoever, that the probability of B given A was the same as the probability of just B happening by itself, these two events are independent, which confirms what our common sense tells us. In number 3, we're asked to consider driving over 85 miles per hour as our first event, and then the second event is getting in a car accident. So what's the probability that I do get in a car accident when I was driving over 85 miles per hour? So this is one of those situations where there's no way to really determine a classical probability here. You just kind of have to use your common sense and judgment. This is a case of subjective probability, and say, does it seem to be the case that driving this fast would potentially contribute to whether or not you get in a car accident? And most likely, we would say that the probability of getting in a car accident, given that you were driving over 85 miles per hour, more likely to occur than just your standard probability of getting in a car accident. So, because it's more likely to happen when your speed is higher, these would be dependent events.